So here we are going to study now the relationship between enthalpy and the work done. Delta H is the enthalpy change, delta U is the internal energy change, P delta V is the work done. So we know by definition that H is equal to U plus PV, or delta H is equal to delta U plus P delta V. We consider delta H because we cannot measure the absolute value of enthalpy H. If the system under consideration is an ideal gas, then by the equation of state we have PV is equal to nRT. For a system in an initial state, temperature remaining constant and there being an infinitesimal difference in the pressures of the initial state and the final state, the equation is written as PVI is equal to NIRT, where I, this subscript, stands for initial. After the system does work of expansion isothermally and reversibly, the final state of the system changes to the parameters PVF is equal to NFRT. The subscripts denote the state of the system, I equal to initial, F equal to final. Subtracting now this equation 1 from 2, we have got P into Vf minus Vi is equal to RT into Nf minus Ni, or P delta V is equal to delta N RT. So we have got delta H. Now we are going to substitute this value. Delta H is equal to delta U plus P delta V. So delta H is equal to delta U plus delta N RT. What then is the difference between enthalpy and the internal energy and heat? Mathematically, we know that U, internal energy, is equal to Q minus W, where Q is the amount of heat exchanged between system and surrounding. W is the work done by the system on the surrounding or the surrounding on the system. H is the enthalpy. It is equal to U plus W, and that is internal energy plus the work done. Now, what is Q? Q is equal to the heat absorbed or the heat lost by the system. It is given by a formula Q equal to M into C into T2 minus T1, where M is the mass of the system, C is the specific heat of the matter in the system, T2 is the final temperature, T1 is the initial temperature. H is equal to Q only if the pressure for the transition of state from initial to final condition is constant. That the difference is so infinitesimally small, we assume it to be steady or almost constant. Which difference? The pressure difference from initial state to final state, because a gas is going to go for reversible isothermal expansion. Now a few examples will make the concept of enthalpy pretty clear. First, enthalpy of combustion. We are going to study the different types of enthalpy I told you. First one is enthalpy of combustion, and in this what we are seeing is that there is this enthalpy of combustion is denoted by delta Hc. It is defined as the enthalpy change that accompanies a process of combustion of 1 mole of any substance. It implies that combustion reactions are always exothermic and spontaneous or non-spontaneous. Well, combustion reactions are mostly exothermic and spontaneous. Look at this natural event, forest fires in Australia. You have got compost fires anywhere where you have got composting. These forest fires in Australia are mainly due to the hot, dry weather with drought-like conditions and the lightning together that sparks off a fire, a combustion process. It causes a release of large amount of heat. In case of compost fires, the bacterial decomposition of the compost often generates heat. The moisture and the pressure inside that builds up due to the resulting organic gases such as methane and the carbon dioxide causes the compost to combust spontaneously. The organic matter have low ignition point and tend to shoot up into flames. Now comes a question. What is ignition point? Let us continue. If you, however, think of certain reactions in chemistry that are called combustion reactions and they are exothermic and yet they need energy for sparking them, why should it be then at all exothermic? It could have been considered as endothermic. These reactions appear non-spontaneous and endothermic because they are taking heat to start the process. The process just needs to get initiated as the energy barrier for the reactants to react needs to be overcome. The energy released soon overrides the input energy and the reaction is highly exothermic. Such reactions are said to have a negative enthalpy of combustion. The initial heating is required to generate enough heat in the system to sustain the reaction of combustion. The temperature at which the system can become self-sustaining in the combustion reaction is called the ignition temperature of the substance or the fuel. Another term that is of importance in combustion reaction is the flash point. It is that temperature at which any inflammable substance can have enough vapors that can catch fire when an igniting source is brought near it. This is unlike the ignition point, where the source of heat is required to convert the substance first into its vapor, then that it will sustain that heat and it will often override the igniting heat or the sparking heat. The combustion process with generation of large amount of heat is then sustained by the system. When we have to calculate the enthalpy of combustion, we don't always have a handy data on the various parameters. For example, the enthalpy of combustion in the following reaction is given as delta Hc. Acetylene, when it reacts with oxygen, it gives out carbon dioxide and water. The heat of combustion or enthalpy change in combustion of acetylene is minus 1309.5 kilojoules. This I have taken from a data from the internet source. In the next reaction, combustion of 1 mole of glucose, calculate the enthalpy change of combustion. How do we do it? I shall show you how we can calculate the enthalpy change of combustion. We'll soon see it in the next slide, and here the details for the standard enthalpy of formation for the different reactants and the products are given. The answer finally comes out to be minus 2815.8 kilojoules per mole.